Hello, time for another Man in Gray book review. Today's book is The Quantum Mystery by John Gribbin, published in 2016 by Amazon. It's only 40 pages long. This is part of Amazon's Kindle Singles series, a series of short ebooks. John Gribbin is a British astrophysicist and prolific science writer who's probably best known for his book In Search of Schrodinger's Cat, which is about quantum physics or quantum mechanics. This little book describes a famous experiment that had a huge impact on the theories about what light is, the nature of light. So first, a little background. In the late 1600s, early 1700s, there were two basic theories about what light was. Isaac Newton argued that light was made up of a series of little particles. He called them corpuscles. And he thought that light was made up of little particles because of the way that light is similar to the way a ball bounces. If you take a basketball, for example, and you make a bounce pass on the ground, if you bounce the ball at a 45-degree angle, it will hit the ground and bounce the opposite direction at a 45-degree angle. The two angles are the same. Well, the same thing happens if you shine a beam of light into a mirror. If you shine the light at a 45-degree angle, the light will bounce off the mirror at a 45-degree angle. And so this convinced Newton that light must be like tiny little balls, tiny little corpuscles that strike something and ricochet off, just like a ball would bounce off a wall or a floor. That wasn't the only theory. There was a rival theory developed by a Dutch cloth merchant and amateur scientist named Christian Huygens, and he argued that light was a wave. Not a particle, but a series of waves. And his argument was that light bends around boundaries. For example, when the moon is full, you don't see 50% of the moon. You actually see 51% of the moon because the sunlight bends slightly around the curvature of the moon and backlights part of the moon. So you can actually see a tiny little sliver of the back part of the moon. And so he argued that, Huygens argued that light must be a wave. Much like water waves bend around a boulder. If there's a boulder in the middle of a river, you can see the water waves bending around it. If you're on a waterfront and there's a pier, you can see the water waves bending around the posts that hold up the pier. So these were the two theories, but because Newton was so much more famous than Huygens and regarded as the greatest scientist of his day, most people accepted the particle theory. Then in the early 1800s, in 1803, a brilliant young Englishman named Thomas Young came up with this experiment called the double slit experiment, which cast doubt on the particle theory. Thomas Young was kind of a polymath. He did all kinds of interesting things. It's a shame he's not better well known. He helped decipher Egyptian hieroglyphics. He came up with the first correct explanation for how we see light. He was the first person to explain how astigmatism works, what causes astigmatism in the eyes. He came up with a formula to calculate the dosage for medicines for children. And he had an important role in coming up with a math equation to explain elasticity of solids. How much can you stretch a solid before it will break or warp and not go back to its original shape? But his most famous contribution was in the area of light. He was convinced that Huygens' theory was the correct one, that light was a wave. So he took a piece of cardboard and took a razor blade and made two little slits in it. And then he shined a beam of light through the slits and put a screen up on the other side. When you do that, you see a series of dark and light bands. And what's happening there is the light from one side of the slit is interfering with the light from the other side. This is caused by interference. When the light waves are in sync with each other, you get what's called constructive interference, and you see a beam of light. When the light is out of sync, they cancel each other out. The waves cancel each other out, kind of like acoustic dead spots in a badly designed concert hall. And then you see a series of dark bands. So when you have constructive interference, you have light. When you have destructive interference, you have dark. And so you have a series of light and dark bands. So this showed that light had to be a wave because particles don't interfere with each other. Right? If you take two basketballs and throw them at each other, they don't interfere with each other. They just ricochet off. Right? And so this convinced people that light was a wave. And so everybody said, well, Newton is wrong. In this case, light's a wave, not a particle. And everybody was happy until the late 19th century, about 100 years, 90 years or so after Young's time, something else was discovered that cast light on the wave theory, and that was the photoelectric effect. The photoelectric effect occurs when certain light shines on certain metals. It produces electric current. We call these solar cells or photovoltaic cells. They're used for all kinds of devices. There's solar-powered radios and various devices that use solar power. We see it all the time. But for scientists, the photoelectric effect created a real problem, because what happens is when you shine a really bright, let's say, red light on a solar cell, it produces a certain amount of electricity. If you shine a dim blue light on the same solar cell, you get more electricity. Well, that didn't make any sense. If light's a wave, the brighter the light, the more electricity you should get, because the more waves are slamming into the piece of metal. And why would a dim blue light produce more electricity than a bright red light? Why would the color make any difference? Well, the guy who solved this problem is, of course, Albert Einstein. This was one of his papers that he published in 1905. And his paper on the photoelectric effect was the one that won him the Nobel Prize. It turns out that what Einstein did is he combined the two theories, the wave theory and the particle theory. Light is still a wave, but it comes in packets. It's kind of like if you think of a loaf of bread. If you think of the loaf of bread as a wave, but inside the wave, or inside the loaf of bread, there are slices, right? You don't buy individual slices of bread, you buy loaves of bread, but inside every loaf there's slices of bread. So if you think of the slices of bread as packets, and the whole thing is a wave, and that's kind of what we're talking about here. These little packets of light waves are called photons. And Einstein argued that some photons have more energy than others. The closer the waves are together, the more energy they have. Blue light, purple light, and ultraviolet light has more energy than infrared, red, or yellow light. And so, to give you kind of an analogy here, if you put on some boxing gloves and you start punching a punching bag, if you don't hit the bag very hard, it doesn't matter how fast or how many times you punch the bag, it's not going to move very much because you're not hitting it very hard. But if you haul off and slam in your fist into the punching bag as hard as you can, it's going to move, even if you only hit it 2 or 3 times. And that's like violet or purple light. It has a lot more energy, and so when the particles hit the solar cell, they produce more electricity. This is why if you put blue or purple lights on plants, they grow faster because there's more energy, and so photosynthesis is sped up. And this is how you can get roses to bloom at the proper time. Roses are often sold at Valentine's Day, Mother's Day, and so by putting roses under purple lights, you can get them to bloom at a certain time faster than they would normally. So this basically solves the issue of whether light was a wave or a particle. It's actually both. It's a wave and a particle, but it turns out it's more complicated than that, because further experiments showed that the way you observe the light determines whether it's a particle or a wave. It acts like a particle when you do one set of experiments, and it acts like a wave when you do another type of experiment. And that's basically what the quantum mystery is why should the observation matter? Why would it matter at all that you observe something, right? If you're playing a baseball game and somebody hits a ball and you look up at the ball and you run back to catch it, the ball doesn't change when you look at it. It's still the same ball, and it's still making the same path. But light changes its whole fundamental nature depending on how you look at it and what experiments you do. And that's the second part of this book explains that. And there's still a mystery that can't really be solved here, because quantum physics and relativity, the two main theories that we have of physics, are incompatible with each other. Einstein's relativity theory explains large things like black holes and galaxies, or the top of black holes and galaxies, and quantum mechanics explains things like the bottom of a black hole and subatomic particles. And the theories both work, but they don't work for the opposite situation. Quantum mechanics doesn't explain large objects, the behavior of large objects, and relativity doesn't explain the behavior of subatomic particles. And so we have two theories that work, but they're not compatible with each other, and so that means they're not complete, and that's where the mystery comes in. So if you're interested at all in modern physics, quantum physics, this is a really good book. It's only 40 pages, so it's a quick read. You can read it in less than an hour. It only has 1 or 2 equations. It's not full of scientific, technical talk. It's very accessible, and it will give you a little bit about the history of light. We take light for granted. You flip a light switch, the light comes on. You don't think anything about it, but light is very, very strange. It's one of the strangest things in the universe in the way it behaves. And its lifespan, because light moves at the speed of light, it doesn't age. So photons never age. They don't grow old and decay the way other things do. So if you're interested at all, this is a very good book to start you out on the idea of quantum mechanics in a way that's non-technical and easy to understand. The book is The Quantum Mystery. The author is John Gribbin. This has been another Man in Gray book review. Thanks for watching.